Have you ever really stopped to think about the incredible engineering that's hidden inside your own body? I mean, we see amazing man-made structures all around us, but honestly, some of the most mind-blowing designs are the ones we walk around with every single day. So, today, let's dive into one of the most brilliant examples, your hip. To really appreciate just how clever this design is, we need to understand the conflicting jobs your hip has to do. It's basically trying to solve two completely opposite problems at the exact same time. Okay, so on one hand, the hip needs to be incredibly stable. I mean, for us to walk around on two legs, it has to be a rock-solid foundation. In fact, it's the hardest joint in the entire human body to dislocate. But at the very same time, it needs amazing mobility. It lets your legs swing forward, backward, out to the side. So how in the world do you build something that's both a fortress and a superfluid pivot point? Well, that dual mission creates a really tricky design problem. It's a puzzle that has to be solved before you can even take a single step. Let's really look at the core challenge here, but from an engineer's point of view. See, here's the thing. Your body weight coming down from your spine doesn't line up perfectly over the main shaft of your leg bone, the femur. It's off-center, it's off to the side. Now, if your femur was just a straight pole, this off-center load would create a huge structural problem. And to solve this, your body uses a classic engineering structure, the cantilever beam. Just think of a balcony or a diving board. It's supported on one end, and the other end just juts out into space. Well, the very top of your femur, the neck and head that plugs into your hip socket, it acts exactly like one of these. To make this crystal clear, let's use the perfect analogy, a simple construction crane. It has the same cantilever design, and you know what? It faces the exact same forces as your femur. But this design has a major built-in weakness. So here's a breakdown of the forces at play. As the weight pulls down, it creates a bending force. This puts the top of the beam under tension. It's literally stretching it. The bottom gets squeezed, that's compression. But the real danger, the most dangerous force of all, is right there at the junction. It's a shear force, and it's trying to slice that beam clean off. And yep, if you put it under enough load, that's exactly what happens. The beam just snaps, right at that high-stress corner. This is the fundamental flaw of a simple cantilever. It's basically designed to fail at its weakest point. And this brings us right back to our own bodies. Because that weak corner on the crane, that is a perfect stand-in for the neck of your femur. By its very design, it is one of the most mechanically stressed parts of your entire skeleton, and it's constantly battling those exact same bending and shear forces. So how do you fix this? How do you get around this fundamental weakness? Well, human engineers figured out a really elegant solution centuries ago. But here's the cool part. It turns out nature had the exact same idea and got there first. The fix is just brilliantly simple. You add a diagonal support called a strut. This little strut is a total game changer. It takes all those destructive bending and shearing forces and converts them into simple compression along its own length. And that's a force it can handle easily. This one little addition makes the entire structure immensely stronger. Okay, so that's the man-made solution. What about us? How does our own femur keep itself from snapping under the load of our own body weight every single day? And here it is. This is the moment. Nature does the exact same thing. Look at this. On the left, you've got the engineer's strut. And on the right, that's the inside of a human femur. It's not solid bone. It's this incredible web of tiny bone struts called trabeculae. They create a natural internal support system, a biological version of the exact same engineering solution. The proof is just wow. It's astonishing. When you actually overlay the diagrams of the forces acting on a crane onto a cross-section of the femur, the lines match up perfectly. Those tiny bone fibers are precisely aligned along the lines of tension and compression. It is a structure literally built for the exact forces it has to deal with. So what this all reveals is a really profound principle about how our bodies are put together. It's not random at all. It's a dynamic, incredibly efficient system that is, quite literally, built for force. Let's see how it all comes together. So let's just recap for a second. Your femur is not some solid, heavy lump of bone. No, it's a precise piece of architecture. Those internal fibers, the trabeculae, act like perfectly placed struts. They follow the lines of force to resist both squeezing and stretching exactly where they need to. And the result? It's a masterpiece of efficiency, maximum possible strength for the minimum possible weight. If you take away just one single thing from this, let it be this simple, powerful idea. Bone is built where force flows. Your skeleton is constantly rebuilding itself to be strongest exactly where the stresses are greatest. It's like a living blueprint of the forces that act on your body. So, the next time you go for a walk, just remember this. Your femur isn't just a bone. It is a sophisticated, self-optimizing structure that solved a classic engineering problem with an elegance that rivals any bridge or skyscraper we've ever built: the mechanical axis. Now, this isn't the physical center of the bone itself. Think of it as the actual line of force, the true path that your body weight follows from your hip joint all the way down to the ground. Okay, this diagram spills all the secrets. See that angled line? That's the femoral shaft axis. That's the physical center of your thigh bone. But now look at the other line, the one labeled mechanical axis. See how it's more vertical and it runs slightly inward or medial toward the center of your body? It's deliberately off-center, and that is the stroke of genius. All right, so just to be super clear, let's lock this in. The mechanical axis is not the center line of your bone, and it's also not perfectly vertical. It's this very specific, slightly angled line. And the reason why it's designed that way is the whole key to understanding how we walk so incredibly well. Which brings us to the fundamental challenge our bodies had to solve: the single leg stance problem. Walking is basically just a series of controlled falls. With every single step you take, you are balancing your entire body weight on one leg. This creates a massive stability problem. How on earth does your body keep your pelvis from just tilting over and dropping every time you lift a foot off the ground? Well, if our bodies had gone with that simple, straight line design, we'd be in big trouble. The muscles on the side of your hip, your abductor muscles, would have practically no leverage. It would be like trying to turn a really tight bolt with a tiny, tiny wrench. You'd have no power. Your pelvis would drop with every step, and you'd have to waddle to get anywhere. But of course, our bodies figured out a much smarter, much more elegant answer. This is the off-center solution. And here it is. This is the fix. By shifting that mechanical axis inward, toward the center, our body creates a natural lever, what engineers call a moment arm. Remember that tiny wrench? Well, this design is like giving those hip muscles a big, long-handled wrench, which lets them easily counteract your body weight and keep your pelvis perfectly stable and level. So let's just recap that, because it's so cool. 1, the off-center axis creates leverage for our hip muscles. 2, that leverage allows them to balance our body weight with very little effort. And 3, the result of all that is a system that just massively reduces how much energy we have to spend to walk. It is all about optimization. And this all points to a really core principle of biomechanics. Our bodies will almost always choose efficiency over perfect symmetry. Okay, but wait, there's one last little piece to this puzzle. You might be thinking, I get why it's off-center now, but why isn't it perfectly vertical? Why the extra little bit of complication with the angle? It's because when we're actually moving, when we're walking, the forces acting on our body are not perfectly vertical. Your pelvis sways a little bit, shifting over your supporting leg. Your center of mass moves inward. And that means the force that the ground pushes back up on you, the ground reaction force, it's also coming in at an angle. That slightly angled mechanical axis is designed to perfectly align with all these real-world dynamic forces. There's a quote from the source material that just sums this up perfectly. The mechanical axis is not about symmetry, it is about efficiency. It's not about looking neat and tidy on a diagram. It's about creating the most stable, most energy-efficient system possible for moving us forward. So, what at first glance looks like an imperfect, kind of weird, off-center design is actually the secret sauce. It's the key to us walking around with maximum stability for the absolute minimum energy cost. It is a true masterpiece of biological engineering, and it's happening right under your nose with every step you take. It kind of makes you wonder, doesn't it? What other so-called imperfect designs are hiding in our bodies that are actually another stroke of hidden genius?